Hello and welcome back. In this video, we're going to take a look at magnetic fields and the magnetic forces that are a result of current carrying wires passing through a magnetic field or charged particles moving through a magnetic field. In a later video, we'll take a look at electromagnetic interactions, such as changing magnetic fields that induce electric current without a battery. Let's begin. Now, to summarize these notes, please make sure that you pause and rewind as needed. But do understand that the examples are all going to be done in class together. We are only reviewing the concepts in this video. Section 17.1, the magnetic interaction. What are the two poles of a magnet called? Well, the two poles of a magnet are called the North Pole and the South Pole, much like the North and South Pole of the Earth. Polar, the word polar, refers to opposite. So poles just refer to opposite ends of a magnet. What is the rule for how magnets attract and repel? Like poles repel and opposite poles attract. It is very similar, it is very analogous to opposite charges attract and like charges repel. What happens if you cut a magnet in half? Draw a diagram. Well, let's take a look at that diagram. We can see that if we take a bar magnet, which has a north pole on one end and a south pole on the other, and if we were to cut that in half, we would simply have a smaller bar magnet. Again, with the north pole on one half and a south pole on the other half. And if you keep cutting it in half, you're going to get the same result every time, just simply a shorter magnet. So again, cutting the magnet in half just gets you smaller magnets, each with a north pole and a south pole at opposite ends. The Earth is a giant magnet. If the north pole of the compass needle points towards the North Pole, where Santa Claus lives, then what does that say about the orientation of Earth's magnet? In other words, Earth's magnetic field. Draw a diagram to explain what you mean. Well, it means that the south magnetic pole of the Earth is actually located in the north geographic pole, and vice versa. The south geographic pole is actually Earth's north magnetic pole, creating almost like a bar magnet that looks and resembles this. Describe a brief experiment that shows the strength of the magnetic interaction decreasing with distance. So basically what we do is we bring the south pole of a magnet closer and closer to a compass needle, and you will see the north end of the compass needle start to attract the south pole of the magnet. It might look like this. We have a compass needle that's pretty far away from a bar magnet, and you can see the compass needle, it's kind of starting to deflect towards the south pole. If we bring the bar magnet closer, the north end of the compass needle is really starting to deflect towards the magnet now. And as we bring it even closer, the north end of the compass needle points directly at the south end of the magnet. In other words, decreasing the distance increases the magnetic strength of force. Section 17.2, the magnetic field. We're going to take a few minutes here to actually look at how to draw the magnetic fields, and we're going to use the dot layout patterns surrounding bar magnets on each page. We'll first look at a bar magnet, then we'll look at two bar magnets, a north pole and a south pole, then we'll look at two north poles, and then finally two south poles. And then we'll take a look at electric current passing out of the page as drawn by a dot and into the page as drawn by an X. Let's begin. Now, the general rule of thumb is that magnetic fields are always drawn away from north poles and into south poles. So everywhere there's a dot, we're going to draw an arrow away from the North Pole. So we can draw arrows that kind of look like this. Like this. Okay, drawing out, spreading out away from the North Pole of the magnet. And we're also going to draw them pointing in this direction as well. Now, when we get to the middle, we're going to draw them parallel to the bar magnet. The reason we're going to do that is because you have to remember we're drawing them out of north poles and into south poles. So we have to start angling the magnetic field. These arrows are magnetic field vectors. We have to start angling them towards the south pole, which would now look like this. And realistically, what would happen is the magnetic field lines, as you can see, they begin to loop around from the North Pole to the South Pole in much of fashion that looks like this. From North Pole to South Pole. Now, with this activity here, we're going to draw the interaction between a North Pole attracting a South Pole. So very similar. We're going to draw them out of the North Pole. So let's draw a couple that are going out this way. And we'll draw some that are going this way, and this way, So we're radiating our magnetic fields away from that North Pole. Oops. And we're going to draw one straight magnetic field vector that connects. And you can see we're going into the South Pole, so out of the North Pole into the South Pole. Just like this. And if we were to look at the continuous nature of these magnetic field lines, it would look very similar to this. You'd have it going across, over, and basically bridging the gap between the attracting North Poles and South Poles. In the next activity, we're going to look at two North Poles that would repel each other. So let's begin with a couple of field lines that are going out in both directions. And outward away, pointing in all different directions away from that North Pole. And very similar on this side. And what we get is we get magnetic fields that are going to repel each other in the middle so that there is no field in between two north poles, as two north poles would repel each other. Well, the same situation is going to occur with two south poles. They would repel each other, but this time all of the vectors are pointing in to the south pole. Just like this. And so you'd have two sets of magnetic field lines that are essentially repelling each other in the middle, but going in towards both south poles. Well, what about electric current? Well, one of the electromagnetic principles that we know is that moving charges create a magnetic field. Well, electric current is itself moving charge through a conducting wire. And the way it works is the magnetic field wraps around the current carrying wire in the direction of the magnetic field passes in a circular direction that is going to wrap itself around the current carrying wire. So if we were to use what is called right-hand rule number 2, this is the one that we saw in class that resembled this right here. I call it hitchhiker's thumb. And the eye goes in the direction of current, and the fingers are wrapping in a circle in the direction of the magnetic field. And so, if the current is coming out of the page, that means your thumb would be coming straight up at you towards the ceiling. If you look at the curvature of your fingers, they would naturally wrap around in this direction right here. So I is out of the page, and the magnetic field, is wrapping around the current carrying wire in a counterclockwise fashion. If the current is going into the page, you then take your fingers, curl them up, but take your thumb this time and point it down into the page towards the floor. If you do that, you'll see the fingers wrap around this X, the wire, in a clockwise manner. Now, in this exercise, we're drawing the diagram that shows the cross-section of the solenoid. Now, a solenoid is nothing but a whole bunch of loops, much like a coil or a slinky, really, but it's essentially a coil that you pass a lot of current through, and the magnetic field will essentially pass through the middle. We will do these together in class so that I can show you a little more specifically how to do right-hand rule involving a solenoid. The electric field always points away from positive charges and towards negative charges. State a rule for how magnetic fields point around a bar magnet. Well, as we discussed earlier, magnetic fields point away from north poles and toward south poles. State the algebraic symbol for magnetic field and the units of magnetic field. Well, the variable is the letter B, and the unit is a capital T, which stands for Tesla. Explain the right-hand rule for determining the direction of magnetic field around a current-carrying wire. I call this right-hand rule, or RHR, number 2. And we put our thumb, again, in the direction of current, and our fingers will wrap circularly around the current-carrying wire in a circle showing the direction of magnetic field. Explain the right-hand rule for determining the magnetic field inside a current-carrying solenoid. Well, in this one, we're going to place our fingers through the loop, one way or the other, through the solenoid, through the coil, in the direction of the magnetic field. We do this by sticking our thumb in the direction of the current as it passes through the coil. Again, we will demonstrate this one in class together. Section 17.3, magnetic force exerted by a magnetic field on a current-carrying wire. Using observational experiment 17.2, clearly explain the circumstances under which a magnetic field exerts a force on a current-carrying wire. Well, it was noticed that a magnetic field, when it is perpendicular to the direction of current, the magnetic field exerts a force, a maximum force, on the current-carrying wire. The right-hand rule for finding the force on a current-carrying wire, this is right-hand rule number 1. And the pointer finger goes in the direction of field. The thumb goes in the direction of current. So it still goes in the direction of current or the motion of the charge. Thumb always goes in the direction of motion. And the finger, the bent finger, the middle finger, is the force, which way the magnetic force is pointing. The equation that relates magnetic force to a current-carrying wire and the strength of the field is F force equals BIL times the sine of theta, where F is the magnetic force in newtons, B is the magnetic field in Tesla, I is the current in amperes or amps, L is the length of wire in meter, and theta is the angle between the motion of the charges, the current, and the direction of the field, which would basically be in your right hand the angle between your thumb and your pointer finger, which most of the time is perpendicular. Do keep note that if the current is perpendicular to your field, then that means you're talking about the sine of 90 degrees. And the sine of 90 degrees is 1. So when the field is perpendicular to the current, F is equal to BIL, because BIL sine of 90 is 1, and 1 times BIL is just BIL. So the equation will short to this, it'll shorten to that when the field is perpendicular to the direction of motion. Okay, we're going to be skipping the wire on springs demo. So make your way over to page 9, section 17.4, magnetic force exerted on a moving charged particle. The equation that results is F equals BIL. This is the equation for a current-carrying wire. Now, sorry, this would be QVB. Little typo there. Where F is the magnetic force in newtons, B is again the magnetic field in Tesla, V is the velocity of the particle in meters per second, Q is charge in coulombs, and angle is still the angle, theta is still the angle between the motion and the field, which is still the angle between the thumb and the finger. The finger pointer is still the magnetic field. The thumb is still the motion, but motion is now velocity instead of current. And the finger is still the force. So the rule still applies. Okay, now if you're talking about a negatively charged particle, like an electron, we would use left-hand rule for a negative charge, and all the other parts are the same. Finger is still, the pointer finger is still the magnetic field, and the thumb is still the velocity. But for positively charged particles, we use a right-hand rule. briefly explain how a television CRT display works. CRT stands for excuse me, cathode ray tube. Electrons are fired through a region that has an electric field and a magnetic field that are oriented so that an electron can move straight as the electric force and magnetic force can be balanced in the first region. So in this region here, we can have a region where you have both an electric field and a magnetic field at the same time, allowing the electrons to move straight line. Once the electrons arrive at the deflection coil, then you're going to reach a second region where only a magnetic field is present. And when charged particles move in a magnetic field, they curve due to a magnetic force. Hence, the electrons will be curved and deflected to hit a portion of the screen and excite the pixels in the screen. And that happens at near the speed of light, so several, thousands of image pixels can light up instantaneously, showing a picture on the screen all at once. We're going to be skipping the television demo, so please make your way over to past page 11. We're going to do the example of page 11 in class, but go to the bottom of page 11 if you would, please. Briefly explain how Earth's magnetic field shields Earth's atmosphere from charged particles approaching from the sun. Well, charged particles from the sun are known as cosmic ray particles. Well, the Earth's magnetic field acts to deflect those particles, and it also adds protection in terms of absorbing those particles as well. Okay, in this example, we have a charge Q of mass m moves with speed v in a uniform magnetic field. The velocity of the charge is perpendicular to the field. Write the expression for the following. The radius of the circular path as follows. Keep in mind, magnetic force is centripetal, so we start there. Start with the idea that magnetic force is centripetal, which means we have our magnetic force equation, which is QVB equal to mv squared over r. When we cancel one factor of velocity from both sides, and we solve for r, we get that r is equal to mv divided by qb. What about the period of the charge's circular motion? Well, v is equal to 2 pi r over t. That's the uniform circular motion equation of circumference divided by time. And if we switch those, we get period is equal to 2 pi r over velocity. Well, we can replace r with the value right here of mv over qb, and you can see one of the factors of v cancels on both sides, leaving us with the period is equal to 2 pi times the mass over qb. What happens if a charge enters a magnetic field at an oblique angle to the field direction? Explain why the charge does this thing using basic physics principles. Label the diagram as necessary. Well, as we stated earlier, both the BIL equation and the QVB equation are attached with a sine theta part. And the theta represents the angle between the motion and the field. So if the motion, the velocity or the current, is less than perpendicular, then the sine of theta will be less than 1, which means the magnitude of your force will be less. So when we go perpendicular to a field, we're getting maximum force. If we're going parallel to a field, if we should be, for instance, moving parallel or alongside this magnetic field, well, then theta would be 0. And sine of theta is also 0, and that means 0 force. So you have to be moving at some angle relative to a field, but the smaller the angle, the less force. The closer to 90 degrees from the field, the closer to maximum magnetic force. We will take a look at this concept example in class on the bottom of page 12. We will take a look at the example at the top of page 13 in class as well. Section 17.5. Magnetic fields produced by electric currents. What is the equation that gives the magnetic field strength created by a current-carrying wire a distance r away from the wire? Well, it's B equals mu naught times I over 2 pi r. Let's break this down. What is mu naught? Mu naught is referred to as the magnetic permeability. It's a constant, and the value we use for it in calculations is 4 pi times 10 to the negative 7 Tesla meters. It actually makes doing problems with magnetic fields very easily because the 4 pi is always going to cancel with the 2 pi to reduce it to a factor of 2. So that part actually makes it pretty easy to use. We will do these examples in class together, as well as these examples. We will do this example at the top of page 14 in class as well. Please make your way to page 15. And we have a compare and contrast table between gravitational fields, electric fields, and magnetic fields. Okay, symbol-wise, gravitational field is noted as the acceleration due to gravity. It's the same symbol, g. Well, the electric field symbol, which is also a vector quantity, is denoted with a capital E, and the magnetic field is denoted with a capital B. The units for G would be meters per second squared, but it's also newtons per kilogram if we're talking about the strength of the gravitational field. It's also newtons per coulomb for electric field, and Tesla for magnetic field. For gravitational fields, acts on objects with mass. Electric fields act on objects with charge. Magnetic fields act on charge and velocity. So specifically, we need to be a moving charge, not just a charge. That's the key difference between electric and magnetic fields. Well, gravitational fields are created objects with mass. They're created by objects with mass. Electric fields are created with objects with charge. Magnetic fields are created from moving charges, like electric current. Okay, moving charges create magnetic fields. The basic equation for that relates force and gravitational field is F sub g equals m times g. This is analogous to F sub E, electric force, is equal to Q times E, which is also analogous to the magnetic field one, which is F equals QVB. And yes, there's a sine theta if the angle is less than 90, or F equals BIL if we're talking about a current carrying wire. The basic equation for the strength of the gravitational field is G equals big G times m divided by r squared, is very analogous to E equals kq over r squared, and B equals mu naught I, mu naught times the current, over 2 pi r. Section 17.7, flow speed, electric generator, and mass spectrometer. Putting it all together, what does a mass spectrometer do? Well, it helps to determine the mass of ions, molecules, or elementary particles. It can also help determine the relative concentration of atoms in different isotopes. It works when you ionize gas. So we ionize, hot gas becomes ionized, and these ions are accelerated through a potential difference, and they pass through a region with both an electric and magnetic field, and they're able to move in a straight line in this particular region. Then just like a cathode ray tube inside of a television set, they then enter a second region where there's only a magnetic field, in which case they will move in a circular path because charged particles curve circularly in a magnetic field. Where, meaning the location of where the particle hits a detector or film, is an indicator of its mass. And this would be why, if we look at the equation we set up earlier, R equals mv over qb, if the mass is bigger, the radius is bigger, meaning bigger curve. If the mass is smaller, the radius is smaller. So the mass of the ion, molecule, particle, whatever it is indicative of the radius of the curved path that it makes in the uniform magnetic field region. Now the velocity selector portion is the part right here where you have a region of electric and magnetic fields that are running perpendicular to each other to get balanced electric and magnetic forces. Again, we will do both of these examples in class together. Bottom of page 17, magnetic dipoles, monopoles, ferromagnetic, paramagnetic, and diamagnetic materials. If a magnetic monopole exists, what would it look like? Well, magnetic monopoles have not been shown to exist. Now, that doesn't mean they don't exist. It just means there's no evidence for them. However, if it did, it would essentially be a magnet with only a north or a south pole, but not both. If an atom is a magnetic dipole because of the spin of electrons in its orbit, draw a nucleus with an electron orbiting it and draw the direction of the magnetic field. Well, essentially, if you have an electron orbiting a nucleus, it's going to create, because the orbiting electron is essentially a flow of current, it's a flow of charge, and electric current creates magnetic fields. So all atoms essentially are creating small magnetic fields due to the rotation of orbiting electrons around a nucleus. Now, if you put that together and you get the magnetic fields pointing in certain directions, you then get a magnetized object, which is where we get into the concept of magnetic domains. So magnetic domains are essentially tiny regions of a magnet that are made up of essentially groups of atoms, where all those atoms agree on the direction in which the magnetic field applies. So let's say you have some object, any object, doesn't matter what it is. Pretty much the magnetic domains are going to be very randomized, all sorts of directions. In other words, you, me, the pencil you're writing with, the computer you're using, they're all made of atoms. And atoms have spinning electrons around them. And essentially every object in nature is going to have many magnetic fields that make up the sum of its parts. The problem is, of course, those magnetic fields are all pointing in randomized directions, and therefore they have a canceling effect and a net effect of essentially zero magnetic field. Well, some materials, mostly metallic, but some materials, when you place the object near a strong magnetic field, the magnetic domains all align themselves in the direction of the magnetic field and then temporarily become magnetized. This is true with many metallic objects. And so we get into three types of magnetic materials. Ferromagnetic materials are ones in which the domains align with the external field very strongly. Those would be your metals. Like an iron nail, for instance. If you were to take a piece of metal and heat it up, and bang it really hard, okay, under extreme heat. Just bang it, bang it, bang it. But as you're banging it, you bring it near a strong magnetic field, you might be able to lock in the magnetic field direction into that piece of iron, essentially creating a permanent magnet. That happens in the earth, and that's why some materials, some rocks in the ground are magnetized. They're originally formed from molten lava that has heated or cooled over time, and as it has heated or cooled, it has been under the influence of Earth's gravitational field, and it locks in that direction of that field with the magnetic domains, and therefore it becomes a permanent magnet in the ground. Now, paramagnetic materials will have their domains aligned with external magnetic fields very weakly, so they're not going to be strongly aligned. Diamagnetics are going to have their domains point in opposite direction to the magnetic field. So what would these look like? Okay, so all three substances are shown below to have magnetic domains before an external magnetic field is turned on. Once the magnetic field is turned on, the external magnetic field points to the right. Draw the arrows over the old arrows to represent the new direction. So a ferromagnetic material, like a piece of metal, in the presence of a strong external magnetic field, would all point to the right. Because remember, the external magnetic field, we were told, points to the right. So each one of these arrows that's pointing randomly would all instantly direct themselves to the right. And this would become the north pole of the magnet. This would become the south pole of the magnet. A paramagnetic material, well, it would weakly align itself, which means a lot of the arrows would point towards the right, kind of, sort of, but you'd have some that were pointing in other directions too. And a diamagnetic would completely be pointing in the opposite direction, in other words, to the left. I hope you found this useful. Please make sure that you pause or rewind as needed.